visual picture of the architecture. I wanted to give you a feel of it. So for our understanding, we have, for the mathematical convenience and for the understanding convenience, we have unfolded, okay, your RNN architecture over the time for the better understanding. But remember, it's a physically it is just a one block. Okay, just consider as a one block. Okay. This is how your structure is like this. Because at every time instance, we are giving the input sequences and we are generating the output sequences. And the side x of t. So this is your LSTM block. Yeah. Assume that this LSTM block is designed for 256 neurons. There's 256 neurons. There are 256 targeting units are there. The first kind of design, okay, the first kind of design, what we have done, many to one. The meaning of many to one is, many means I mean your input you are going to present in the form of a sequence. For the naming convention, it is being called as many to one. Okay, literally it's a many to one. Your input is a sequence, but your output is not just one. Means what? This one is a vector. Okay, hereafter we are going to coin the terminology a many to one with more meaningful representation. So the many to one representation I'm going to call as, early we represented this as many to one, right? Understand, your many means it is a sequence, input sequence. The meaning of one is the output you access in the form of a vectorized representation. Input is a sequence, output is a vector. What is the meaning of input is a sequence, output is a vector? We have done a couple of exercises on this, isn't it? One for the numerical, another for the text data. So whatever your text sequence, you have to prepare your text sequence. X of 1, X of 2, X of 3, X of 5. Okay, the email conversation. So whenever we present this X of 1 as the first token, your model will try to bring X of 2. Okay, your X of 2 is given as the target during the learning process. Every architecture you should understand during the learning process what happens. Once after the learning, during the production environment, how it behaves. That way, each and every architecture, if you visualize and keep it in mind, you will have a very good clarity about all three architectures, and also you can easily think about any kind of application. You can immediately think and connect. Okay, for this application, I can really use this kind of design. For this kind of application, I can use this kind of design. So that mind mapping, you can easily do it to try to figure it out. Such a visual mapping. For that understanding, I'm just giving you a quick overview of already the two type of design what we have seen, and today the third design of architecture what we're going to see today. So first let us understand this architecture during the training process. So during the training process, how this architecture will learn. When I feed the first token, your model try to generate the next token, because it is a language model. It has to understand the sequence. It has to understand the sequence, this flow. So when we present the first token, we will be trying to get this output. But why we call the output is a vectorized? Because every time your y cap of t is a vectorized representation based on your vocabulary, isn't it? For the word sequence. If my vocabulary is 4000 vocabulary, the size is 4000 by 1, which is 1 hot encoder. When you present your first token, of course, remember your each and every token is embedded representation. It is a 100 by 1. If I use a 100 by 1 representation, it's embedded representation. So for this is the first token, and you are expecting this is the next token. In the target, the respective position, say for example, the second token is the target, and the position is 2104. Okay, that is one hot. The remaining are cold vectors. With that target, we try to generate the output. And what is the probability we are expecting is 100% probability. But in the first shot itself, your model will not give you 100%, maybe some 0.42 or 0.36 like that. Our motivation is to record the loss. What is the loss? In the first instant, it will record the loss when the first token is given. That loss is recorded. So it is a summation of, isn't it, for the first token, from the first token till the tx of the number of tokens is being fed in the input. So you have to summate this loss. And once the entire sequence is presented, the total loss is computed based on the total loss, total gradient, and based on error gradient, we adjust the weights, the same backpropagation. So here you should understand the output is vectorized, means your output is vectorized in the form. Here, it is a language model. So my output should be one hot encoded according to the number of vocabulary in the corpus, training corpus. So the next we present x of 2 to generate x of 3. Then we present x of 3 to generate x of 4, x of 1. So in that manner, your model will, over a course of time, your model will try to understand after this token, what should I produce? After this token, what should I produce? So like this manner. So here, every time, this is one sentence, right? This is the first sentence. Then second sentence you try. Third sentence. You have thousands of sentences. That is the thousands of training records. This is the training records. Training records. Each records, training record, you are going to have a fixed length of your fixed size of your tokens. If one of the training record is very short, you know the procedure. We have to pre-pad with zeros. Okay, pre-pad with zeros, and actually here this is literally your x of 1, x of 2, x of 3 stars. So that is why we call such kind of model as your many to one means your input is a sequence, okay, and your output is a vectorized representation. So the same idea we are extending for the sentiment analysis. I told you, just copy paste a few reviews from Google reviews or Amazon or Flipkart, some e-commerce portal, and try to assign a positive or negative or even multi-class, a good, average, poor, something like that. That also your input is a sequence, okay, because all the reviews are with a fixed length sequences. Okay, the maximum sentence, maybe you can fix it like a 15 token is the maximum length of the sentence, and all the sentences you pre-pad with zeros and make it using pad sequence. You make it a fixed size. You train the model. In this case also your output is vector, but here the output, the size of your output vector is not equal to the size of the vocabulary. That is not my objective. Here my objective is to classify the reviews. So output here also, output is a vector, but it's based on the number of classes. If it is a binary, like a positive and negative review, it is a 2x1. So it is one hot encoded like this. Okay, whenever you present positive reviews, your target should be like the 1, 0. Whenever you present a negative review, your target will be like 0, 1. So remember, this model is trained to produce one next immediate token at a time. To produce one token at a time. So whenever you try to, we figure it out like nice to. When I feed this as an input sequence, our model is learned in such a way that after this, here. So in a production environment, what we do, whatever the next token is produced by the model. Okay, your model try to use this here as the next, as part of the sequence. It's try to append this guy in a production environment. Nice to hear. Okay, what is the probability of the next token given? If it is a nice to hear, in what manner it has learned, it will try to predict which token should have the highest probability. So it will try to get nice to hear from you. That is the sentence you are trying to generate. So your model will try to predict the next token. So once it predicted the next token from is the predicted value. So naturally we organize your production environment in such a way that whatever the value is predicted, again that will get appended. Like this time, nice to hear from will go as an input sequence, and it will ask the model to say what is the probability of the next token. Nice to hear from you. That way, you can have a feel of a continuous sentence is generating. But remember, at one point of time, whatever the input sequences you give, your model is trained to produce one token which has the highest probability. And maximum, okay, since this model has trained for 15, okay, it will generate up to the longest sentence it can give. The next token is the length is 15. Beyond that, if the 16th token if you give, the model is not trained for that. So when you train the corpus itself, you try to keep the longest sentence as much as possible. Even you can give 100 tokens. Even practically, even if you don't use 100 tokens, but still LSTM has the capability to remember the long sequence. So you can keep the size is the 100 is the largest one. Even a very long sentences also you can produce. It will not complain that hey, I cannot accommodate the 16th token. 16 token size I cannot give the output. Okay, to avoid that kind of issue, keep the size to the maximum as much as possible. So this is what a sequence to vector representation. Even the same model, we have solved one numerical problem also. We have kept 2 months trading data. Okay, every time the 2 months trading data. This time the output is, though we called as a vector, but in this case as a regressor problem, we are solving as a regressor. You can consider your output as just 1 cross 1. Typically it is a scalar. Okay, since it is a regressor problem, we are treating this as a 1 cross 1. So in general, this kind of design architecture is called sequence to vectorized representation. So this is one special case for the numerical data, because as a regressor problem, no need to vectorize this output. So we keep this output as a scalar. So this is one exceptional. But all other application which comes under this case is a representation of a sequence input and vectorized output. Can you able to appreciate this? Why it is called a sequence input, vectorized output? Any question on this? In the next design, what we have seen, we have used 2 different LSTM. Okay, both are individually going to act as a language model. This is also one LSTM. So individually trained. How these guys are individually trained is something like many to, okay, individually, if you look at individually, it is being trained like many to one vector, because when this model should learn the sequence of English sentence sequence it should understand. Similarly, this LSTM should understand the sequence of French sentence it has to understand. But both are interlinked, tied together. For this LSTM, okay, the initial state like your C of t and A of t, okay, it will start with a random initialization 0. So that is what any standalone LSTM, that is the way it will start learning. When the first token is presented, again here also you have a fixed sequence. Okay, the first token, second token, third token, and so on till the last token TX. So the idea of this, how do we train this? Whenever we present this, your model should try to, because anyhow, we are not going to use this model for the next word prediction. But however, I need the memory of that. In what way it remembers that sequence, that I need that memory, because that memory is going to give me what kind of English sentence is this model has learned? What order of the word tokens this model has learned? So that information I'm communicating to this guy as an initial state for this model. So when this model start learning, it will start learning with not with the zero initialization. It will start with the C of t and A of t states of this. So return state true. That is why we give a return state true. So C of t and A of t is being presented to this. That means this LSTM is going to start learning by considering this as the initial state. So why we are talking about this side of the LSTM, we are talking as the decoder side of the architecture, we are talking as a vector to sequence. Okay, that your input side is a vector to output side is a sequence. That is the way this has to be get trained. That means what? Initially, when we train the model, okay, what is the vector here? So here the vector is the start of the sentence will be given some unique identification, a unique integer representation for this, because already this guy has this LSTM has been already trained in such a way that so whenever this LSTM is started with this is the initial state, okay, with a trigger token. This trigger token is again it is a vectorized, okay, vectorized, and this input is coming in the form of a vectorized form of the input, and how it is for the particular English sentence during the training process, we know the corresponding French tokens need to be produced, right? The first word of the French token will be given as the target vector. The first word, what is the translation should start from this. That is the reason we have created one more variable when we prepare the data set. Okay, that is your output sentences input. So output sentence is input. So SOS is the input, the first token of the French translation. When here the first, so this is the first word. Okay, then the first word is being given in the form of a vectorized form. It has to learn to produce y cap of 2. Okay. Actually, we are not presenting the input in the form of a sequential manner. That is what you should understand. Okay. During the training process, we need this sequences in the output. I am expecting this model to produce y cap of 1, y cap of 2, y cap of 3, and so on. To produce that sequence, first of all, I should train this guy, right? So during the training process, whatever the value this guy is going to produce, that is going to be tied as the input during the production environment. But during the training phase, I know the entire sequences what this guy has to produce in the output. Okay, that we call this the teacher forcing phenomenon. So what need to be produced in the output sequences, I know the actual sentence already. So in the next instance, this value will be taken as the input to the next time instant. That is how you prepared the input to the output sequences. In what way you prepared the input? So your input is prepared based on SOS is the first token, the first translation token, and this is the first translation token, the second token of the translation, and this is the third token. Till the time if the model produces the corresponding vector representation for, we have assigned one vector representation for the EOS. Okay, the moment the model has produced the vector representation for the EOS, the model will understand the translation is completed. So this is the sequences I'm expecting in the output. So during the training process, only for how you can comprehend this whole decoder process as a vector input sequence output to the context of in a production environment. In the production environment, how it is behaved. In the production environment, during the training process, we know the actual sequences. So we are presenting the token here and to produce this. But in the real production environment, Okay, this is unknown to the model, right? This is unknown to the model. That is why we reconfigure the model to receive one token. That is the reason we reconfigure the model to receive only during the training phases, the entire sentence is known to me. So during the production environment, only the model is reconfigured to receive just one token, which is a trigger token SOS. This guy will be fed as an input along with this is the initial state. It produces a translation token. That translation token will be taken as input and it will try to produce the output like this. So this way, this process, we can do it in two manners. One is by setting this decoder side LSTM as return sequence true. Okay, a return sequence true. This will be taken care automatically in a production environment. Otherwise, manually also you can write the coding in such a way that you remember like the email text generation, what we have done, a small subroutine we have created. Every time the model produces an output, that output should be appended as part of your input sequences. Whatever the output is produced, that has to be appended as part of your input. Now the whatever the new value, whatever is predicted, that is appended and that is being fed as an input and it's producing the next one. So in case if you don't specify this return sequence true, even afterwards also you can achieve this by manually setting this, whatever the model, because remember at one point of time, this is going to produce only one token. Only one token. So according to the French vocabulary, we have got 9,432 something. Okay, out of this 9,432, which is the token gets the highest probability will be predicted first. If you have specified return sequence true, automatically this value will be fed as the input to this. It will trigger the next token. So when this value is being predicted, okay, this y cap of 2 will be predicted in such a way that, okay, what is the probability? Okay, which token to be predicted here? Given SOS and our previous example we have used lessee, right? Lessee, SOS and lessee. This is going to give the for the tomber. It is giving the high probability for that. So it produces after lessee, it produces tomber, and so on. So this value is automatically taken as it's appended to the input, and it is generating the output till the EOS. Even if you don't specify this as part of your hyperparameter, manually also you can do the setting when you are operating this model in a production environment. Just you have to append every time whatever the model dot predict, you are using this as a model dot predict. So the predicted value will get appended to the input. As part of the input, it has to be appended where the